And as well, we'd like to thank all of our partners and recognize them for their contributions, both intellectually and support otherwise. Without these folks, these webinars would not be possible, and the work that's being done would not be possible as well. So thank you so much to these folks. Okay, so today's webinar format, we're in the Zoom webinar format if you're not familiar. This webinar will be recorded and will be available at this website, friendsoftheyampa.com, after it is uploaded at the conclusion of the webinar. And you can also find, I believe, the past webinars if you've missed them from this, this series earlier in the summer at the website as well. So all conference attendees are automatically muted. So if you've noticed that you're trying to say something, we won't be able to hear you. If you have a question for the panelists, we ask that you send these questions through the Q&A box located at the bottom of your window. If you're on the phone, hit *9 for Q&A. If you have a question more on the technical side of the Zoom webinar format, we ask that you type those questions into the chat box, which is different than the Q&A box at the bottom of your screen. And we'll have someone fielding those questions in real time, whereas the Q&A will save those questions until the discussion portion of the webinar. And if you prefer to speak your question rather than having your question read, please use this raise hand feature, and we can facilitate that happening as well. All right, so just to give a bit of a background, now in its third year, the Yampa Basin Rendezvous, if you're not familiar, brings together local experts, top scientists, on-the-ground practitioners, and engaged community members to explore the various demands on the Yampa River's water, people, and culture. And we're really interested in learning how these needs are met and where challenges remain. This is primarily done through dialogue with the local community, and we really hope to pair research with the community's intimate knowledge and expertise on the challenges and successes of conservation and use practices on the Yampa, so we can really identify how additional climate and weather information and research may be suitable for making strides on the Yampa itself. And so this year's webinar series has really been focused on measuring and managing seasonal variability. Last webinar, we talked about the fact that our techniques and our instruments that we've relied on primarily for streamflow and water resources forecasting aren't providing the same quality of information in a changing climate. Today, we're going to turn our discussion towards shifting seasons and precipitation. So we're experiencing shifts in seasons and precipitation with climate change, and today our panelists will explain what some of these changes are that we've seen and how these changes impact our local and statewide watershed health, and begin to point towards a discussion on how such information can be implemented into a climate adaptation framework. So it's my privilege to introduce today's panel to you. I'll just do brief introductions here, and then we'll do a more in-depth introduction for each speaker as they begin their talk. But we've got great representation from across the US today. We bring Professor David Stahle, distinguished professor from the University of Arkansas, as well as Russ Schumacher, who's an associate professor at Colorado State University, who wears several hats as well, and Courtney Peterson, doing some really interesting research out of Colorado State University as well. And just to remind folks that the format will be panelists will give their talk, and then we'll have time for maybe a clarifying question before we move on to the next panelist. But we'll really save all of the more in-depth questions until the conclusion, and we have our dialogue portion at the end of our third panelist. And a reminder that you can type your questions into those Q&A boxes, science-related questions. Okay, so without any further ado, it is an honor to be introducing Professor David Stahle to you. Professor Stahle is a distinguished professor in the Department of Geosciences at the University of Arkansas in Fayetteville, and he received his PhD from Arizona State University. Professor Stahle's current research is really focused on tree ring and tree ring chronologies, and he's doing some amazing work both in the Pan American region, looking at tree ring chronologies in the Amazon, as well as looking at tree ring reconstructions of seasonal to storm level precipitation totals in California as well. He's a leader in the field, and we are very thankful to have his perspective at the Yampa Basin Rendezvous this year. And so with that, I will turn it over. Thank you so much, Dave.
Thanks very much for having me. Can you hear me?
Yes, sounds great.
Okay, thank you very much. I'm Dave Stahle, University of Arkansas. I'm going to give a little paleo perspective on seasonal moisture variability over the United States and North America. Title is Tree Ring Reconstructions of Soil Moisture and Seasonal Precipitation for North America. And we illustrate here the network of tree ring chronologies now available for North America. You know, so there are over two.
We can't see your screen yet.
Pardon me?
We can't see your screen yet. Do you mind resharing it? Sorry about that.
Now, do you see it?
Yep, I see the PDF, and I see you're about to go into full screen mode, I think. So this is perfect. Thank you.
Hello, do you see it now?
I think it's still transitioning to full screen mode. Maybe we can give it just a second. It took a second last time. I don't see it quite yet. I'm also happy to share my screen instead if you prefer, Dave. What do you think?
Well, let's get it going. Yeah, I guess so. You know, will you be able to advance it for me?
Absolutely.
Hello.
Okay, please go ahead and I will be happy to advance the slides for you. Sorry. Oh, so
Okay, sorry about that.
No, I'm sorry. This is my fault. I put it into slideshow view. Okay.
Oh, let's go back to the beginning, please.
Oh gosh, okay. Thanks everyone for your patience. I really apologize about this. Okay.
This is the third slide. Here we go. Hello?
Yep, please go ahead whenever you're ready. Again, I apologize about that.
My fault, probably. Tree ring reconstruction of soil moisture, seasonal precipitation totals for North America. This is the network of North American tree ring chronologies. There's now over 2,000 of them, you know, from the tropics to the Arctic. I mean, it is I argue, the finest high resolution paleoclimate data set in the world. It provides direct extension of the instrumental record of soil moisture and precipitation into the pre-instrumental era for over 1,000 years. There are now over 2,000 tree ring chronologies available in this region. Each one of them is based on dendrochronologically dated time series. So they're exact. Each ring is dated to the exact year in which it was formed. And there's typically 40 cores from 20 trees at each location. So we're talking tens of thousands of trees have gone into this network. Most of them are correlated with soil moisture, available soil moisture and or precipitation. Certainly that's true for the United States and Mexico. We break it down into the species, the principal species that have contributed to the chronologies available for the eastern United States. So several species of white oak, post oak, chestnut oak, also hemlock, bald cypress, and several other hardwoods and conifers. Out west, the network is based heavily on ponderosa pine, Douglas fir, blue oak here in California, and various other conifers. The red shading are tree ring chronologies that I and my lab have developed. So this has basically been my life's work here in Mexico with my friend and colleague, Jose Villanueva. So with this network of proxies that sense soil moisture in particular, we've developed these drought atlases, what we call drought atlases, and the first one being the North American Drought Atlas. So please advance the slide and I'll show you a comparison of tree ring reconstructed Palmer drought severity indices during the most famous drought in American history, the Dust Bowl drought. And so what we're looking at here is the so-called North American Drought Atlas. And it's both instrumental data, it includes the instrumental data from 1895 to present, and then tree ring reconstructed data that go back 2,000 years, at least over some parts of the continent. And so what we're looking at here is the Palmer Drought Severity Index for summer for the decadal average of the Dust Bowl, 1931 to 1940. So the hot colors are indicating drought of increasing severity, and the cool colors, wetness of increasing intensity. And what we've done here is we have taken the gridded Palmer Drought Severity Index data on a half a degree grid. So there's like 11,395 grid points, behind this isopleth field. And in the case of the instrumental data, we've simply averaged the PDSI data for summer. So PDSI is, of course, a measure of soil moisture based on precipitation supply and temperature / evapotranspiration demand. And in the case of the reconstructions, we've taken tree ring chronologies proximate to each of the 11,000 some odd grid points and used Ed Cook's methodology of principal component regression to develop reconstructions at each grid point. They've then been averaged and isoplethed. So that's basic, that methodology has basically been Ed Cook's life's work as well. And when you compare these two, and that's why I'm showing this, you can see the great fidelity with which the trees reproduce both the spatial pattern and intensity of this most famous of all American droughts. When we had coast to coast dryness from the Atlantic to the Pacific, and what's really the worst drought of the 20th century, and the tree rings tell us that in fact, this was the worst drought in the last 350 years, at least until recently, at least until the turn of the 21st century. And modeling is suggesting that in fact, human activity, the breaking of the sod on the prairies and so forth, the lofting of dust, the contribution of dust from human sources to the Dust Bowl may have actually aggravated the climate anomaly of the Dust Bowl, made it more intense and more prolonged, maybe making, the Dust Bowl drought of the 1930s one of the first great anthropogenic droughts in world history. So this is a very famous drought, and this slide illustrates the fidelity with which tree rings can reproduce, soil moisture anomalies. The trees don't lie. They're really telling us something fundamentally true about the history of climate. And so this North American Drought Atlas can be accessed online, at this website. Dorian Burnett, our colleague, has developed these wonderful web tools where any user, they're super user friendly, can go in and make a map for any given year. You can make a map for any given sequence of years, like 1931 to 1940. You can use the instrumental data, or you can map the tree ring reconstructed data, which of course is 10 times longer than the instrumental record. That's the virtue of the tree rings, this long prehistoric perspective. Or you can take out any one grid point and plot the time series. Or you can extract a region and plot the time series for that. You can do correlation analysis, composite analysis. It's a super functional website that's open and available to us all, whoever might be interested. And anyway, the North American Drought Atlas has recently been updated. And if we can advance the slide, I'll show you this latest article that, or the principal figure from this latest article using an updated version of the North American Drought Atlas to place the current drought over southwestern North America in the perspective of the last 1,200 years. So the paper was led by Park Williams at Lamont Doherty Earth Observatory and Ed Cook, of course, the developer of the NADA. And they provide here a smooth estimate based for southwestern North America of tree ring reconstructed soil moisture. So there's the average condition down the middle horizontally. Anything above the horizontal line is wetness, below is drought. So this is a soil moisture indicator. And it's been smoothed for the regional average, a 19-year smoothing. And the purpose of this article is to argue that the early 21st century drought, the 19-year period from the year 2000 to 2018, in fact, was a period of deficit precipitation. But it was kind of a garden variety deficit in precipitation. It wasn't that intense. That level of dryness in reduced rainfall have been seen, or precipitation more broadly, have been seen many times over the last 1,200 years. But the warming, the accelerated warming that's happening over the southwestern United States has transformed this garden variety precipitation drought into a soil moisture drought that is the second worst mega drought in the last 1,200 years. And so here they draw the threshold across the bottom of the current 21st century drought back 1,200 years. And you can see that only the 16th century mega drought exceeded the current drought in intensity. So, and the idea is that this may be evidence for a anthropogenic contribution to the current drought. And in fact, of course, the way this works is, escalating air temperatures, warmer air can, of course, hold more moisture. It can demand more evaporation off the hydrated land surface. It can demand, the atmosphere can, more evapotranspiration off the vegetated surface and forest in particular. And the result is drier vegetation, drier forest. And this is certainly part of the contribution to the mega fires that the country is currently suffering across the Southwest. And the argument is that the current drought is due to both natural climate variability, augmented maybe as much as 47% of the current drought has arisen from this escalating anthropogenic warming. So the rest of this talk is going to concentrate on this epic drought of them all, the 16th century mega drought, because tree rings provide the prehistorical perspective. So if we can advance the slide, I'll show you these new reconstructions. I'll show you the data that went into these new reconstructions that are part of this North American seasonal precipitation atlas. So it turns out that the 2,000 some odd tree ring chronologies that are available across North America include a subset of chronologies that have a discrete seasonal signal. In fact, there are 439 tree ring chronologies as located on this map that are significantly correlated with precipitation totals, from December through April. That's how we're defining the cool season. in this case, and this is their spatial distribution. And there's another 547 tree ring chronologies out of that 2,000 total that have a discrete correlation with only the warm season, defined in this case as May through July. And so we can use these two different networks of tree ring chronologies to reconstruct precipitation on a seasonal basis over the last, well, mostly it's about 600 years. Over the Southwest, it goes back fully 2,000 years. And the way this works, well, partly it's like in California, it's a winter dominant precipitation regime. So all of the tree ring chronologies are only correlated with winter, and antecedent winter precipitation can recharge the soil moisture and favor tree growth, you know, and so we've got a very strong winter signal in a lot of these tree ring chronologies. But we also have early wood and late wood and total ring width chronology. So the early is the spring wood component, and it tends to be correlated with precipitation in spring and prior to spring. And then we also have late wood chronologies, and that's the summer wood component of the annual ring, and that tends to be correlated with summer. So we've used these discrete seasonal signals, you know, to reconstruct a seasonal precipitation atlas for both the winter and the summer. And we can look in the next slide at the 16th century mega drought from a seasonal perspective, this being the worst drought in the last 1,200 years, fully 24 years from 1568 to 1591. And the North American Seasonal Precipitation Atlas is telling us that it was a super intense cool season drought over the southwestern United States. And in Colorado in particular, it was only a cool season drought, and the warm season was actually near normal. In fact, looking at these maps, it strikes us that this 16th century mega drought may actually have been the result of three different regional droughts. First, this winter season drought over the Southwest, extending into the Southeast and up into the Northeast, which bears a strong, at least over the Western United States and Mexico, bears a strong spatial resemblance to the kind of forcing associated with the cold conditions in the Eastern Equatorial Pacific, the famous La Nina conditions. Of course, La Nina events don't last 24 years, but that is very much a La Nina-like spatial pattern of drought during the cool season in the 16th century. Second, we have this Midwestern drought that looks like the kind of drought anomaly pattern you typically get with the positive phase of the Arctic Oscillation. When the jet stream is shifted north, you get subsidence over the Midwest, moisture divergence, and lower May through July precipitation totals typically arise with the positive phase of the Arctic Oscillation. And then in Arizona and Sonora, you know, at the, you know, dryness at the northern periphery of the North American monsoon, the so-called Mexican monsoon. So we think that the North American Drought Atlas and the North American Seasonal Precipitation Atlas, you know, demonstrate the value of these proxy tree ring data. You know, in the first case, you know, to provide examples of drought and wetness extremes and seasonal regimes that challenge our understanding of climate dynamics and climate modeling. And secondly, they provide an important, you know, perspective on emerging anthropogenic climate change from the perspective of natural climate variability over the past millennium. Thank you.
Thank you, Dave. There's one clarifying question, and then Mike can take back over. But I'm Lindsay, and I'm with Friends of the Yampa as well as the Yampa River Fund. And we have a question from Elise, and she asks, where do the soil moisture and precipitation data come from for these sites?
Well, there are several data products available, and there's, of course, the National Oceanic and Atmospheric Administration, NOAA. They have PDSI data. The Global Precipitation Climatology Center provide precipitation data. In the case of the North American Seasonal Precipitation Atlas, it's the GPCC data that we've actually reconstructed.
Great, thank you. And for the sake of time, we'll move on and there will be more questions answered at the end.
Wonderful. Thanks for addressing those questions, Lindsay. And thank you for a really fascinating talk, Dave, and for sharing the North American Drought Atlas. And that website tool sounds really interesting. I know that I'll be tooling around over there after the webinar is over. Thank you so much for giving us that perspective on the deep historical context of sort of the seasonal dichotomy between wet and warm seasons and what can happen with respect to drought and mega drought in particular. We now transition from those wonderful triggering chronologies into a bit more of the current history and present. And doing that will be Professor Russ Schumacher, who's an associate professor in the Department of Atmospheric Sciences at Colorado State University. And in addition to his faculty position there, Russ serves as the Colorado State Climatologist and the director of the Colorado Climate Center. Russ received his bachelor's in science with majors in meteorology and humanities from Valparaiso University in Indiana, and his master's and PhD from the Department of Atmospheric Sciences at Colorado State University. Russ's research includes extreme precipitation, weather systems, the climatology of precipitation in Colorado's weather and climate. And he's been a member of the CSU faculty since 2011. We're so excited to have you with us here today, Russ. Thank you so much for spending the time, and we really look forward to your talk as we get the screen sharing sorted out. Thank you so much.
Right. Yes. Well, I'm happy to be here and see if it works on my end. Okay. Look okay, and you can hear me?
Yes, looks good.
Great. Well, yeah, thanks so much for the invitation to be here and to kind of, step forward then from, Dave provided this great long historical perspective and some of the historic droughts in Colorado, and we'll now kind of zoom in on that more recent period and especially the very recent period here to look at what's been happening here in the last few years and try to put that in a little bit of context as well to I think bring that back to some of the points that Dave was making. Before getting into that, just for folks in the Yampa Basin that might not be familiar with our office and what we do, a super quick history of the Colorado Climate Center. So it's been here at CSU since 1973. Prior to that, there was a federally funded state climatologist program, but then the states were kind of left to figure it out on their own at that point. And so in Colorado, we've had it as part of the Department of Atmospheric Science since 1973. And I've been in this role almost 3 years now as the state climatologist. And our mission is to provide climate expertise for the state through climate monitoring and climate research and climate services. And I guess I'll probably be doing a little bit of all three of those as we go through the talk here. Here's a picture of our team. Some of you might be familiar with the tall guy in the back here, Nolan Duskin, who was my predecessor and he's mostly retired, but still around and works part-time to kind of give a great historical perspective with the wealth of knowledge he has. All right, so we'll begin with, I always like to start with this because I think it's useful to just take a look at the incredible variations that we have across our state. This is the annual average precipitation in Colorado from the PRISM data set, which incorporates precipitation gauges, of course, but then also takes into account the effects of the terrain on precipitation that are reasonably well known. And so, what we can see is everything from the high desert of the San Luis Valley with 7 or so inches of precipitation each year to the Park Range in northern Colorado, and which feeds the Yampa Basin primarily, with some spots over 40 or 50 inches of precipitation each year in the form of snow, of course, and then all the kind of wild variability in between the mountains and the valleys on the western slope, between the Palmer Divide and the Arkansas Valley on the eastern plains, and sort of all sorts of other things that you can pick out there in terms of where our precipitation falls and the huge variations we have. And then what that also means is we have huge variations throughout the year. And so the topic here we're focusing on, of course, is seasonality. And this map tries to, it maybe looks a little bit like some abstract art, but kind of tries to represent that seasonality. And what it shows is the month that on average we see the maximum precipitation at each location. And Colorado is the only state that has all 12 months represented on this map. I think Utah gets 11, and a couple other western states are close. But in any case, you can see Eastern Plains not so variable, mostly May, June, July, August throughout the Eastern Plains, the summertime, spring and summer rainfall. The low elevations of the West Slope, the maximum rain is in the fall, generally, September, October. Then you get in the mountains and it's a little bit of everything. The northern mountains, including the mountains that feed the Yampa Basin. Some spots are January, some February, some December in there. Some of the southern mountain areas are more February, March, and a little bit of everything in between. So it gives you a sense of how variable that seasonality is, even when you're just looking at sort of what our average conditions look like. And then from year to year, that can change quite a lot. And just to look at that in a slightly different way, this shows I'm going to show January and then August, the proportion of the annual precipitation that comes in those couple of months. And so this is for January. The scale here basically shows if you're up in these dark green colors, which don't show up on this particular map, it'd be something like 15+% of the annual precipitation falling in that one month. Or if it's in the dark brown, then it'd be like less than 1% of the annual precipitation in that month. If it was evenly distributed, 1/12 is like 8%. So it's kind of that would be in the white colors. You're near that. So this is January, and the Eastern Plains it's very dry in the winter generally, but this is when the northern mountains really get their big precipitation, is in the winter, of course, during the snowfall season. And so we can kind of see that here on this map, that the northern mountains and much of northern Colorado west of the divide are getting quite a bit of precipitation in the winter. If we switch that to the summer months, it kind of reverses in that this is August. And much of the Eastern Plains, especially the Southeastern Plains, the San Luis Valley, and Southwestern Colorado get, on average, the benefit of a lot of precipitation from the North American monsoon. But that's actually not really true in Northwestern Colorado, in that there isn't a very big uptick in the summer in Northwestern Colorado like there is in Southwestern Colorado. And we can see that from, just as an example, this is the normal distribution of precipitation throughout the year at the Steamboat Springs weather station. And you can see, the peaks in sort of December, January, and then in the spring, April, May, but then it comes down in the summer. Whereas if we looked at Grand Junction, for example, theirs goes down in the spring and then comes back up in the summer. So the monsoon is a little bit less of a factor on average in Northwestern Colorado, but of course that's still, 1.5 inches, 2 inches of precipitation on average in the summer months. Okay, so let's kind of look then at not our super long record of tree rings that Dave was showing, but our instrumental record going back to the late 19th century. This is statewide for Colorado. We'll zoom in on the Yampa Basin or Western Colorado in a minute. This is the statewide annual average temperature through last year, and we can see the well-documented warming trend over the last 120 years or so, and an acceleration of that trend in the last 30 years or so. And of the 12 warmest years on record statewide, we've seen a big number of those coming since 2000. If we look at Western Colorado, it's kind of the same story. This is just for the climate division that's basically west of the divide, all the parts of the state that drain into the Colorado River eventually, and we can see a similar picture there with warming trend over this whole period of something like between 2.5 and 3 degrees Fahrenheit per century over that period. If we look at, and in Western Colorado, those numbers are even a little bit more, they stand out a little bit more, where of the 14 warmest years on record, 11 have occurred since the turn of the century. If we look at precipitation though, there's actually not really a long-term trend statewide, but you can pick out some of those, wet years, with much of the 80s and 90s being relatively wet in Colorado, and then some of our more recent droughts, 2012 or 2002 and 2012 and 2018 being bad. But then you also see some of those periods like the Dust Bowl period that Dave pointed out in the 30s there. And there's not actually a long-term trend in annual precipitation statewide. And similarly, that's true for Western Colorado. You can see it's essentially a flat trend, but with huge variability for annual, or this is for water year precipitation in Western Colorado, with some very wet years and some very dry years mixed in there. But we'll break this down a little bit more here in a second. Okay, so what does this warming mean, again, in the context of seasonality, and what does it show? And this is a graph that takes a second to explain, but I think it's quite illustrative once we sort out what it means. And so the two lines that are shown, so these are just you can kind of a rolling seasons of 3 months, going from November, December, January, February, and so on. The blue line here shows the standard deviation, or the variability in temperature over the course of the year. And so what we see, for example, is, and this is like from year to year variability. And so we see that's huge in the winter and into the spring, in that, the variability of temperature we can have here in Colorado can be extremely variable in the wintertime, whereas in the summer, that's not so much true. It's just sort of, varying levels of warm or warmer or a little bit cooler. So the variability is much lower in the summer. And then the reddish orangish line here shows the observed warming trend over those seasons on the same scale. And so you can see it varies some from season to season, but not all that much. But what we want to point out here is, kind of in the summertime, these two lines are very close to each other, meaning that the warming that we've been seeing in summers is going to be a lot more apparent, because it stands out with respect to the natural variability that happens, in that the natural variability in the summer is not that great in the West. But we've seen a lot of warming during that time period, and that kind of points out what the how the summers have been changing is probably more apparent. And that the point being, like, what would have been considered a warm summer 75 years ago is now a cool summer. And I think we're starting to see that, what we thought was a hot summer in the 20th century is starting to happen a lot more frequently. All right, so let's look at this then in terms of drought. Again, we don't have this kind of data going back to paleo scales, but we do have the data that Dave presented. This is the kind of more detailed picture that's been done since the U.S. Drought Monitor was established in 2000. You probably are used to seeing these maps in various contexts. But this is the percentage of the state of Colorado that's been in drought. And really the point here is to just point out these big droughts that we think about, 2002 into 2003, and then 2012 into 2013, and then 2018, and then the current drought that's ongoing now in 2020. But you see almost all the time some part of the state is in drought, but it's these ones where it covers a much larger area that we get concerned about and that have much bigger impacts. The first time we had the drought monitor completely clear was last summer, or late last spring, May into June last year, after the huge snowpack year of 2018 into 2019. But then you can see how quickly the drought has returned this year. Okay, so we've talked about kind of drought conditions and temperature and precipitation trends over time. We're going to zoom in now into basically what's happened here recently, because I think it's illustrative of some of those trends and some of those issues that we're talking about. And we've just ended up this summer that again, we went from reasonable snowpack last winter into pretty severe drought conditions and big fires happening in August when we don't really expect them to happen. And so what we saw is that August especially, and it wasn't the entire summer, although the entire summer was hot and dry as well. But this month that just ended was for Western Colorado, the most extreme hot and dry summer month that we've seen, since we have observations. And I would imagine if we looked in, if we had data going back to the long-term droughts that Dave pointed out, that it would still stand out as extreme. This is the temperature anomaly, how much the temperatures were different from the average conditions for August, the month that just ended a few weeks ago. And this is, these dark red colors here are 5, 6, 7 more degrees Fahrenheit above average, which again in the summer is a huge departure from normal. And it was everywhere on the western slope, being incredibly hot during August. And basically what happened was that the North American monsoon that we expect to occur in July and August did not bring any moisture in, which means not only was there no rain, but there were no clouds, the humidity was low, and that makes it get hot, and that kind of fosters these bad fire conditions. And at some of the long-term, most of the long-term stations in August in Colorado and really throughout the West were hottest on record or very close to that. And if we zoom out, all of these ones on the map here are where it was the hottest August on record. And you can see it was, almost the entire Southwest. And so zooming back into Colorado, then this is kind of where it stood in terms of the records, basically everywhere in this dark red color again it was the hottest August on record for essentially the entire western part of the state. And then if we look at precipitation, it wasn't record dry everywhere, but it was record dry a whole lot of places and very, very dry everywhere else. And so this has really brought out the drought conditions here in the summer. And so if we look at this in the time series of just August and just over Western Colorado, not only was it extreme in terms of temperature, it stands so far out ahead of any other August that's ever been observed. So something like 6 degrees above the 20th century average, but 2 degrees hotter than any other August that had ever been observed. Okay, and so Dave introduced this concept of the standardized precipitation index is to look at how unusual or usual the precipitation is at a given place. It's basically all you do is you fit a distribution to the observed precipitation. If it falls in this part of the distribution, the values would be between -1 and 1, kind of are in the neutral or near normal conditions. But once you get worse than -1, then you're in very dry. And if you're, you know, down into -2 or -3, then that's extremely dry sort of conditions that don't happen, you know, very often at all. And then there's an analogous metric called SPEI that incorporates the effects of evapotranspiration. This is the effect that Dave talked about, where the atmosphere becomes thirstier when it's hotter, even holding all else equal. And so we'll compare these two because I think it really illustrates what's been happening in Western Colorado over the last 20 years or so. All right, so we'll show this for this data set. We can zoom right in on the Yampa Basin here, the Yampa-White Basin that's shown here on the map. And so this is SPI, that Standardized Precipitation Index, the record of that. And this is for 12-month periods for water years. And you can see all the variability that's happened over you know, over time, and you know, big wet years in the 80s, and you know, dry years in the Dust Bowl era, dry years in recent times, but nothing sort of recently jumps out as being historically dry just in terms of annual precipitation, and that fits with what we looked at earlier. Now let's look at summer. And so this is the SPI just for the summer conditions. And you can see summer of 2020, the bar, you know, most on the right over here, was definitely very dry, and you know, up there with the driest summers that have happened in the basin in the past, but not necessarily the you know, it wasn't the worst. It wasn't a record dry summer, but still very bad in terms of precipitation. But now when we bring in the effects of the temperature in the SPEI, including the evapotranspiration effects, this is where the story starts to look very different. And this is where, when we include this effect, this summer that just ended is the worst on record for the Yampa-White Basin, and it's true across much of Western Colorado. And the other thing to note here is the difference in the trend that you see with SPI, where there isn't really a trend over the long term. But then if we look at SPEI, you definitely see those most recent, you know, 20 or so years stand out, that you don't really have any good years in that time period, even though there were some good years precipitation wise. And then if we look just at August to kind of finish up, this is just the SPEI for August. Again, August 2020 for the Yampa-White Basin was the driest on record, but not by that much. You know, there are other really dry years that show up in there. But when you add the effects of the temperature, I mean, look at this graph. That August is so much worse than anything else that has ever been observed in August, and it's the worst summer month for SPEI that exists in the record. And so it shows how truly extreme the summer was this year, and how rapidly the conditions went from, you know, not too bad in the spring to really serious drought by the end of the summer, and you know, the fires and all the other water resource impacts, calls on the river that we've seen. So I will finish there. Just I'll point out there's our website, my email if you want to get in touch, and follow us on Facebook and Twitter. We like to post like interesting weather tidbits about Colorado's climate. And then of course a pitch for joining COCORA's, the Citizen Science Rain Gauge and Precipitation Measurement Network that anyone can join. So I will finish there, and I will try to unshare my screen here so we can move along.
Thank you, Russ. We're going to move on, put the questions at the end. Thank you for your amazing presentation.
Wonderful. Yeah, thanks so much, Russ. That was really interesting context to put this summer we're still living through. Yeah, oh, let's start my video here. So wonderful. Yeah, we'll save questions for the end, and we will move on to our third and final panelist for today, Courtney Peterson, who is a returning champion from a past Yampa Basin Rendezvous. And Courtney's back this year. She's a research associate in the Department of Forest and Rangeland Stewardship at Colorado State University. Courtney is also a member of the Northern Institute of Applied Climate Science. And one of Courtney's major roles is to serve as the Adaptive Silviculture for Climate Change Coordinator, where she focuses on disseminating the ASCC, the Adaptive Silviculture for Climate Change, project findings and translating them into outreach for training opportunities with land managers and scientists working to manage forests for climate change adaptation. Courtney also serves more broadly as a climate adaptation specialist, supporting partners through assistance in climate science communication and adaptation planning, resources, and training. Courtney holds her BS in Natural Resource Recreation and Tourism with a concentration in environmental communication and her master's in Human Dimensions of Natural Resources, both from Colorado State University. Her master's research involved a public perception survey of Colorado State Forest Service management of state and private lands. When she's not working, Courtney loves playing the violin in a local volunteer orchestra, traveling the world to experience new places and any outdoor adventure with her friends and family. And with that, we are so excited to have you back, Courtney, and we're really looking forward to your talk and putting some of these past climate information and present climate information into an adaptation framework. So thanks so much for joining, and we'll get your screen shared and you're all good to go.
Awesome. Thanks so much for that introduction, Mike. And thanks everyone for having me back again this year. It's great to get to talk with you all again. And so as Mike said, I'm going to shift topics just a little bit and provide some information on basically a framework that was developed by the Northern Institute of Applied Climate Science for really taking all of that great science that Dave and Russ just provided, and how do we really distill that down into what can this look like for on the ground climate change adaptation strategies and actions. And so, as Mike said, I am I'm one of a team of climate change coordinators at the Northern Institute of Applied Climate Science, or NIACS, which is led by Chris Swanson and Maria Genoviak out of the Northern Research Station of the U.S. Forest Service. And so we really span the boundary between academic research and the practical information and support that land managers need to really make those climate change adaptation decisions on the ground. And so we're chartered by the U.S. Forest Service, several universities, nonprofits, and tribal conservation organizations. And all of these different organizations have different values and views and perspectives on land management, but agree that a boundary spanning organization like NIACS is really needed when it comes to thinking about climate adaptation and carbon services. And so we provide practical information, adaptation resources, and technical assistance in the following climate and carbon services, including climate change impacts modeling, vulnerability assessments, climate change adaptation, carbon science and management, and science translation and professional training. And so we've got 20 different people, some who are directly involved in technical assistance to stakeholders, and others who are really doing that modeling and research, looking at impacts to tree species and carbon pools and that sort of thing. And so we also staff the Northern Forest Climate Hub, and so we cover mostly the Midwest and the Northeast is that footprint, but since I'm based out of CSU, I've been doing a lot more work in Colorado and the Southwest, and we partner with organizations in California as well, and so we're kind of spanning some of those boundaries and outside of the Midwest and the Northeast. And then just as a bonus, as Mike said, one of the projects that I help coordinate is the Adaptive Silviculture for Climate Change Network, which was the project that I talked about last year at the Rendezvous. And so ASC, or the Adaptive Silviculture for Climate Change Project, is really this network of experimental trials across the US and Canada, where we're really looking at how do you adapt different local forest ecosystems to climate change impacts, and looking at this spectrum of adaptation options from maintaining what's on the ground to really thinking about some of those wild and crazy ideas for transitioning to future conditions. And so I'd encourage you to check that out as well at adaptivesilviculture.org. And so the big question that both NIACS and ASC are trying to answer when we're thinking about climate adaptation is what actions can be taken to enhance the ability of a system to cope with change while still meeting our management goals and objectives? And how can we as managers and practitioners really be developing plans for those actions in a systematic, organized way despite the uncertain climate change projections and risks that we're dealing with? And so when it comes to responding to climate change, if you want a single answer for how to respond, it really is, it depends. It depends on where you're working on the ground and what you're trying to achieve. And so this is where what you value and what your goals and objectives for your management really come into play. And this is where NIACS works, is we meet our partners where they're working to really figure out how to meet your local goals and objectives in an era of climate uncertainty. And so we define adaptation as the adjustment of systems in response to climate change. There's a lot of longer definitions for adaptation, but they kind of all boil down to this. And so what we really want to do is think about ecosystem-based adaptation activities that are building on the sustainable management, conservation, and restoration activities that we're already doing on the ground in the ecosystems that we manage. But again, really focusing on what do you value about that ecosystem and how much risk are you willing to tolerate into the future. And so when we're thinking about adaptation, we kind of think about, especially forests and watershed management, we have a current condition on the ground that we're dealing with and as a starting point. And we also have a desired future condition in mind that we're trying to manage for. And so all of the management that we're doing are really to meet those goals and objectives of creating that desired future condition. However, with climate change, it really pulls that trajectory of what that future condition will look like in an uncertain trajectory over time. And so how do we think about handling kind of that uncertainty that comes with climate change is really identifying different adaptation actions across this broad spectrum of options to consider. And so from resistance on one end, where we're really thinking about reducing impacts and maintaining those current conditions on the ground, and improving the defenses of those ecosystems against change and disturbance, to resilience, where we're really trying to accommodate some degree of change, but then encouraging a return to a prior reference condition following those disturbances that might occur. And then finally to transition at the opposite end of the spectrum, where we're really thinking about some of those forward-looking, wild and crazy ideas, where we're trying to intentionally facilitate change on the ground and enable our ecosystems to respond to those changing and new conditions, like those really extreme August drought temperatures that Russ was just talking about. And so when NIACS started in 2008, we spent a lot of time talking with our partners and our stakeholders across the region to talk about education on climate and carbon, but we also did a lot of listening. And some of the consistent themes that we heard were these 4 challenges to implementing adaptation actions on the ground. And so 1, climate change is too big and too complex. 2, that climate information isn't relevant enough for me and the work I'm doing on the ground. 3, that one-size-fits-all answers are not sufficient. And then 4, that there's not enough real-world examples of managers actually implementing adaptation strategies on the ground that we can be learning from. And so after hearing these themes, what NIACS ended up creating was what we call the climate change response framework. And so this is really a structured, process-oriented framework that works at multiple scales and was really built through time based on the feedback from our partners. And so we try to address those 4 overarching questions through these 4 different components, including partnerships, vulnerability assessments, adaptation resources, and creating those demonstrations on the ground. And so, especially starting with that climate change is too big and too complex, that's really where creating more capacity with really effective partnerships is really important. And so bringing together a bunch of different partners to events like what you're doing through the Yampa Basin Rendezvous are extremely important for helping build that capacity and really brainstorming what can we be doing for adaptation efforts on the ground? And so bringing together those diverse skills and perspectives to work toward those common goals of adaptation. And so really thinking about working across all lands and bringing in some new creative ideas to the table are really effective in creating those partnerships and that trust. And then dealing with climate information not being relevant enough, NIACS provides vulnerability assessments. And so vulnerability assessments were really created specifically for natural resource professionals because they articulated a need for information that really informs them how different tree species or ecosystems might be responding to climate change. And so the vulnerability assessments really try to embrace some of the uncertainty by using a full range of future climate change projections rather than just an ensemble that might overemphasize one potential climate pathway over another. And so we really use this spectrum of projections in combination with different impact models and published studies on the effects of ecosystems and come together in a workshop setting to rate the vulnerability of major forest types within the region for each of these different vulnerability assessments. And then they create basically a baseline of relevant information from which we can then frame our response and really start thinking about climate adaptation actions to implement on the ground. And the key thing about these vulnerability assessments is that they do not make recommendations or address the question of how to respond as a land manager, but instead they provide a basis of some of that information and projections for you as the managers who have the local knowledge and the expertise for the ecosystems you're managing to then take and figure out how you think is the best way to respond to those actions on the ground or to those impacts through your actions on the ground. And then as far as the one size fits all answers don't work for me, that's really where these adaptation resources come into play. And so we have developed basically what we call an adaptation workbook. And it's a flexible workbook approach that's paired with a bunch of different menus of adaptation strategies and approaches. And so it's really designed for a variety of landowners with different diverse goals and objectives. And again, it's not making recommendations, but instead providing a series of options for you to pick and choose from based on what your goals and objectives are for the ecosystems that you're managing. And so our adaptation workbook process is really a 5-step adaptive management framework where we're really starting with defining the location and your management goals and objectives for the ecosystems that you're managing, and then really thinking about how to assess the climate change impacts and vulnerabilities for that location. And that's where those vulnerability assessments and scientific literature and traditional ecological knowledge all come into play. And then we can take those impacts and all of that information and really evaluate our management goals and objectives. And do they still make sense given those climate change projections and the impacts that we're dealing with on the ground? And then if they do, we can move forward and really start to think about identifying and implementing different adaptation strategies, approaches, and tactics for on-the-ground actions. And I'll go into that in a little bit more detail here. But then of course, the last step is that monitoring piece where we really have to monitor and evaluate the effectiveness of our actions and see if they really are helping us still achieve those goals and objectives as we're moving forward under these climate change projections and futures. And so our adaptation menus of strategies and approaches really are a menu of possible actions that allow you to decide what's most relevant for a particular location and set of conditions. And so just like a menu at a restaurant, you don't want to pick everything off of these menus because it's going to be too much. So you really want to use these menus more as a way to pick and choose the strategies and approaches that make the most sense for meeting your specific management goals and objectives for the location and the ecosystem type that you're managing for. And so the benefit of these menus is that they really are a way for us to take some of these broad ideas and our management goals and objectives and connect them to those specific actions that we want to implement on the ground. So they provide kind of this way for us to connect the dots from those goals to the impacts that we're seeing to the actions that we're coming up with and implementing. And then allow us to really make those actions intentional based on all of the information we're getting from the science and the data, that Dave and Russ presented, and those vulnerability assessments and information, and really think about how to strategically start implementing those strategies on the ground. And then it also provides a way for us to communicate our ideas with our stakeholders and different audiences, especially if you're going through NEPA or you really have to communicate with a political leader in Steamboat about how important it is to really be maybe transitioning the ecosystems to something that's future adapted. Then you have this clear intentional thought process that you can use to communicate why the actions you're implementing are really important. And then hopefully they help boost creativity for thinking about some of those wild and crazy management strategies and approaches that we could be implementing to help us adapt to future conditions. And so these adaptation menus of strategies and approaches, again, they're really specific to different disciplines. And so we have a series of published menus from forestry to forest watersheds to tribal perspectives. And we also have several that are in preparation, including a fire adapted ecosystems menu, which is highlighted here, that we worked with the Southwest Fire Climb and Northern Arizona University on to really think about how can we be adapting our management for changing fire regimes that we're seeing. And so they're organized into this tier hierarchy where we're really thinking about those broad adaptation concepts and then getting more specific to strategies and then approaches, and then you as the managers figure out what is the best tactic to implement on the ground for your specific location. And then again, they're thoroughly researched, they're co-developed and tested with partners and stakeholders, and then published through these peer review processes. And so basically the workbook and the menu are part of this logical train of thought that I was talking about to really help connect the dots between our goals and our objectives all the way down to those actions we're implementing on the ground, and then ultimately monitor and make sure that we're continuing to be effective at meeting those goals and objectives into the future. And then finally, with that last question, there aren't enough real world examples of adaptation on the ground. What we've done is we've asked all of the different organizations and partners that have gone through our adaptation workbook process to allow us to convert their responses and examples into demonstrations and then put these online. So you can find a bunch, over 350 projects that have gone through this process across the country, not just in the Midwest and the Northeast, on the NIAC's website, which is forestadaptation.org, and find some of these demos of different managers who are really thinking about how to take these climate change impacts and turn them into these adaptation strategies and approaches and actions, and really have these real world examples that we can be learning and sharing from. And so just one example that I wanted to provide was from Crosby Farm Regional Park, which is also one of our adaptive silviculture for climate change project sites located in the Twin Cities in Minnesota. And it basically is a park within the middle of the city along the Mississippi River corridor, and it's a floodplain forest composed primarily of ash and elm species. And it's got a ton of recreation opportunities. People come there a lot for getting out of the frenzied city life and really going and exploring Crosby Farm. And so some of the goals that they had in mind were really creating this diverse stratified forest canopy with natural regeneration. They wanted to make sure that there's still diverse habitat for wildlife because they're part of a migratory flyway and really want to encourage pollinators with it being within the middle of the city. They also want to make sure that there's some bluff trail restoration and slope erosion control, especially because they are in this floodplain forest. And then also making sure that there's continued monitoring and removal of invasive vegetation, because they deal with a lot of things like smooth brome and different understory and tree species that are invasives to the area that they're trying to manage for. And then some of the climate challenges that they're dealing with, taking all of that information from different vulnerability assessments and using some of the tools that we have, like the hardiness zone maps and the climate change tree atlas. Basically, what they're experiencing are warmer temperatures, especially at night in both the summer and the winter. They also are experiencing increased drought stress in the summer, just like Russ was showing we're experiencing here. There's more heavy rain events and flooding. And so they had a huge flooding event that occurred last year that lasted all the way into, I think, July, which was really unusual for the Twin Cities. And then, of course, we know that they were hit by some of those extreme weather events, including the polar vortex that happened, creating those really extreme low temperatures in the winter. They also have a shift, there's a projected shift in hardiness zones from a 5 to a 6. And so that would create some similar climate conditions to those of Omaha, Nebraska. So those are all different climate change challenges that Crosby Farm is trying to deal with and needs to take into consideration when they're creating these climate change adaptation strategies for on-the-ground management. And so basically using the forestry menu and going through this workshop process in our adaptation workbook and those 5 steps, these are some of the different actions that Crosby Farm decided to implement on the ground. And since it is a part of our experimental trial as a part of the ASCE network, they kind of picked strategies that fall across the entire spectrum from resistance to transition. And so as managers, you might not want to necessarily implement transition strategies, or it might not make sense to still do resistance strategies, but since this is part of, again, an experiment, they're trying all 3 to see which one makes the most sense and works the best moving forward into the future. And so more along that resistance end of things, they're really trying to prevent the introduction and establishment of different invasive plant species and remove existing invasive species. They're dealing a lot with emerald ash borer within the Twin Cities. And again, this is a floodplain forest that's mostly composed of ash and elm. And so really thinking about how to deal with that and maintain some of the values of ash and elm tree species within this forest into the future. They're also thinking about how to incorporate different genotypes of some of those existing native species that might be more adapted to warmer temperatures. There's also honey locust, sycamore, and swamp white oak on the property. And so they're considering some of these different genotypes of these species and planting those. They also want to incorporate a broader range of flood adapted species that are native to Minnesota and to northern Iowa. So really thinking about pulling species from that Mississippi River Basin corridor and thinking about how to work with some of their partners and some of the further south species or further south cities and species that are there to really think about what might be the most flood adapted and planting those. And then promoting a broader suite of future climate adaptive species that are both flood tolerant and drought tolerant to address some of those impacts and challenges they're seeing that might be from seed zones farther south along the Mississippi River. And then finally, they're starting to think about how they might be able to introduce future adapted species that and shift that species composition along the Mississippi River corridor a little bit within the Twin Cities to be similar to areas in southern Iowa and Missouri. So really thinking about that shift in those hardiness zones and what might be the species that might survive the best under those drought and flood conditions moving forward. And so they're testing a bunch of different species and monitoring those to see what's going to succeed. And so I also just want to give a plug for, we're doing some online adaptation planning and practices courses this fall, winter, and spring. And you can sign up for these at this web link here. And so basically these are 8-week courses where we do weekly lectures and bi-weekly discussion sessions and really work our way through the adaptation workbook process. And so you come with your project and your location in mind and your goals and objectives, and we walk through this 5-step process over a series of 8 weeks to really think about how to identify some of those climate change impacts and challenges and opportunities that we're dealing with, and then develop those specific actions to help adapt ecosystems to those changing conditions. And so really, we'll walk through that adaptation workbook process and you walk away with a climate-informed project where you've really detailed your intentionality from your goals and objectives to the actions that you might consider implementing in your project on the ground. And so just some final thoughts from me. One of the key things as managers is we're dealing with all of this uncertainty for climate change, and really, especially with that variability that we're dealing with when it comes to precipitation and that spectrum of emission scenarios, really certainty is a myth, and we really have to start planning for a range of different futures and the projections that we're seeing. So we have to really think about how can we be creative and how can we embrace this uncertainty in the management that we're deciding to implement on the ground now for 50 years into the future. And so tools are really helpful, but ultimately your judgment and your knowledge and your expertise, especially of the Yampa River Basin, is going to be critical and crucial when it comes to implementing some of those climate-informed choices. And also integrating that climate change information might not always be ideal, especially if it comes to we really need to protect a threatened and endangered species within this river corridor. We might not be able to adapt the forest ecosystem or that habitat to future conditions, and we really have to maintain what's on the ground to protect that threatened and endangered species. And so we have to take into consideration, again, that whole range and spectrum of different strategies to implement on the ground. And then being really clear about what your values are and what you're managing for is extremely important, and showing your intentionality on what you're implementing and why, and really connecting those dots. And then really we have to be learning by doing. So we have to start trying these things now, which is why I think the work that NIACS and the Adaptive Silviculture for Climate Change project is really important, because we're really starting to think about what does this management look like on the ground, and what are some of these different adaptation strategies and approaches that we can be trying in different forest ecosystems across the US and Canada. And so with that, I'll stop and I'll open it up to questions. Thanks, everyone.
Thank you, Courtney. If all the panelists that spoke want to show their faces, we're going to actually open this up to not just questions for Courtney, but everyone. I love your presentation about how we can utilize the science and use it to manageable outcomes, I guess. And thank you for presenting on that. And if everyone, we're going to be doing some question and answers, and please stick around. Mike will be coming back to tell you about the next webinar. So the first question, and I know Russ spoke to it a little bit, but perhaps he can add a little. From Lorna says, have we seen changes in North American monsoon over the last 20 or 30 years, 30 years?
Yeah, that's a good question. Can you hear me okay?
Yes.
Okay, good. Making sure I was back. Yeah, that's a good question. You know, if you look further south, of course, that's where the monsoon really jumps out, is like in Arizona. That's kind of where, you know, or into northern Mexico for that matter. But in Arizona, the last 3 years have been really dry, but then there were several wet monsoon years before that. And so I'm not sure that there's any kind of real trend other than maybe a bit more variability, but I'm not sure. I'm not kind of an expert on the details of the monsoon. But if you look in Arizona, that's where the warming effects really jump out, because if you look at any of these parameters like SPEI or vapor pressure deficit, or things that kind of try to measure both the precipitation and the temperature effects, I mean, those wet monsoon years they had several years ago still look like bad years in something like SPEI. And so that, you know, I think that the summer warming is kind of probably the biggest change there. Now, there are some recent studies that have projected that the monsoon will basically decline in intensity, I guess is the way of putting it, kind of weaken that because of warming. But it's, you know, the models aren't super reliable, I think, on that, but that there are some suggestions pointing that these big regions of high pressure, like we saw this summer, kind of keeping all the monsoon moisture out, that those maybe become more frequent in the future. Maybe we're already seeing that. I don't really know. But anyway, I think it's a pretty open area, because it's the kind of thing that climate models don't, at least until recently, are really incapable of simulating very well.
Great, thank you. And we have a comment and question for you again, Russ, from Nathan Stewart. He says, thank you for your excellent talk, Russ. Is the evapotranspiration component of SPEI sensitive to variation in vegetative cover? For example, agricultural lands versus grasslands, or perhaps more importantly, forests by dominant species?
Yeah, that's a good question too. This formulation of SPEI is pretty basic in that it really just it just uses the temperature and the variations in the temperature and things like that to try and estimate that, which works pretty well at a kind of broad brush scale, but probably does not mean a lot at the scale of an individual forest or an individual field. There are other ways to calculate it, though, that do take into account the vegetation type, but that's you almost have to do that with data from individual weather stations, as opposed to kind of trying to do it over this big gridded data set, because you really need to know where what crops there are or what vegetation there is that you're interested in. So yeah, the stuff I showed doesn't try to account for that in any way, but there are ways to do that.
Great, thank you. And the next one is also a comment and question from Nathan Stewart towards Dave. Thank you for your excellent talk as well. I'm curious how tree water deficit and or landscape level forest drought stress might impact tree sensitivity to soil moisture, i.e., are we at risk of this sensor network losing its sensitivity to changes in microclimate as we experience new and perhaps eventually unprecedented drought?
Interesting question. Can you hear me?
Yes, we can.
Okay, very interesting question. In fact, tree rings kind of probably underestimate the severity of drought because trees die in drought. And I think that's sort of one of the implications of your question, at least that's what I kind of hear, is that, so how bad, for example, was the mid-19th century drought over the central United States, or the 16th century mega drought, if maybe 10% of the trees that were alive at that time died in that drought, and therefore they were extremely sensitive to it and responded strongly to it, and yet they're not in our sample. And so, yeah, that's, these are biological organisms. They are responding to the environment. And as the environment changes, their response can change to a degree, especially if environmental variability starts to exceed the range of variability to which those plants were adapted.
Thank you, Dave. And the last one we have, and then Anna Wilson has some questions for you guys as well, but from Tashiana, it says, for Courtney, are there certain strategies your team has found helpful to meet the needs of such a wide range of stakeholders? Can you elaborate on efforts to learn from and collaborate with local Native leaders and other community members to be sure local voices and knowledge are valued through research and workbook writing processes?
Awesome. Yeah, that's a great question. So thinking about strategies across all of those different stakeholders, that's why that first step is so important. So really defining the location and where are we working and who is at the table and what are the overarching goals and objectives. And so really starting with that as the foundation for the strategies that we're coming up with is really important. And so really thinking about what do you want that desired future condition to be for that specific local ecosystem that you're dealing with. And so the strategies are totally going to vary depending on what forest type you're in, or if you're managing for a watershed, or if you're trying to manage for a threatened and endangered species or something like that. And so really having those menus of different strategies, and ones that might be more for, restoration and mixed conifer forests might be something that someone would choose to do because it might encourage some of those fire and drought adapted species within a mixed conifer forest, versus you know, thinking about something where, like the Crosby Farm was thinking about, where they're really trying to do some assisted migration and think about some of those more flood and drought adapted species. So those are just kind of some different examples, but it really depends on the location and what your goals and objectives are in the ecosystem that you're dealing with. And then for efforts to learn from and collaborate with different Indigenous peoples, we have a tribal perspectives menu, and that really stemmed from some of the trust and relationships that had been built already between NIACS and the Ojibwe and Menominee tribes in the Northeast and the Midwest. And so the process of really starting with what they value on the ground and really bringing in their perspectives and their values was really crucial in this process. And so it was, you know, an iterative process with a ton of meetings and a lot of trying to learn the language, and really building that trust and reciprocity was really key and important. And so the menu was developed specifically for Menominee Ojibwe tribes, and it takes their cultural values into consideration and their traditional ecological knowledge and the histories that they have of managing their resources, and really takes that into consideration for some of the different adaptation strategies and approaches as options within a menu. And then again, it ranges from some that are more along the resistance end, maintaining those conditions, to different options that are more of that transition, but really making sure that we're still providing those resources and the values and the cultural values that are needed to sustain their way of life under climate change into the future. And so that trust and reciprocity is really important in making sure that their voices are heard and the lead voices moving through that process throughout the entire process and framework.
Thank you. And there's one more question for you as well, Courtney. Please stick around. Mike's going to talk about the next webinar, and all the panelists agreed to stay 30 minutes longer if you guys want to enjoy a discussion and or have more questions. So the last question for Courtney, how long is the time frame of these projects? How long are you able to build a relationship with the folks reaching out?
Great question. So it just depends on what the managers, again, it depends on what the managers want to do and how much time they're willing to commit. For our adaptive silviculture for climate change project, we're really thinking about actions and monitoring 15 to 20 years into the future, so that we can really collect some solid data on how are the forest ecosystems responding to the management that we're implementing on the ground. Others will go through our adaptation workbook process, and they'll kind of come up with a plan. And the key thing is they know how to use the framework so that they can continue to use it for other projects that they want to implement on the ground. But then we still serve as kind of those technical assistants as needed, and you can continue to reach out to us as you want to, as you continue to implement more strategies on the ground. And so that's more of a time frame where it really just depends on how long you want to continue to engage with us moving forward.
Awesome. Thanks for answering those questions, panelists, and thanks to Lindsay for facilitating that first portion of the Q&A. I just want to jump on real quick as we're pushing up on the half hour. This is when the webinar was scheduled to end, but we've, as questions roll through, our panelists have agreed to spend some extra time with us to field those questions and engage in further discussion. But I did want to call to attention the fourth and last webinar in the 2020 YBR series will be held on October 22nd, same time, 11 Mountain. And we'll be discussing uncertainty and the impacts of shifting seasons and precipitation on the Yampa River Basin. We're still putting together and finalizing our panelists, so that information isn't yet available, but you can find further details at the Friends of the Yampa website, which is listed at the bottom of the screen here. And I just wanted to, if you do have to jump off, just thank you so much for taking the time to be with us today. There's a lot going on in the world, and it's really fantastic to be able to engage in these conversations with you all. So thanks for tuning in, and I will turn it back over to Lindsay to see if there are any other Q&A questions coming through.
Thank you, Mike. We actually have some questions from Anna Wilson. If Anna, you want to come on.
Sure. Thanks, Lindsay. And thanks everyone for these really awesome presentations. I've also received a couple of comments already from participants saying how much they've enjoyed these. I guess the first question I would like to ask is to Dave, and I have a quick question first, which is, in that Nature paper you showed with the really long record, over what spatial extent is that Southwest record representing?
I think, can you hear me? I think it represents Colorado, New Mexico to the Pacific Ocean.
Okay, wow, so that's a really big area too. And then
the greater Southwest, definitely. And a little bit of northern Mexico as well.
Okay, thanks. And then my sort of more in-depth question is about the kind of stands that you mentioned using for the tree rings, like that each place has maybe more than 10, about a dozen trees that you're sampling from. And so I just wondered what kind of, if you see any real variability within those sites, or what kind of extra information comes out of being able to sample so many trees in a given stand.
Usually we sample at least 20 trees per site, and that's kind of a legacy sample size from the old days. Nowadays we're sampling more like 50 to 100 trees, 2 cores per tree, so we're really doubling down on the sampling. In terms of the coherence of the climate response among the different trees, that's a very interesting question. And of course, tree growth as measured with tree rings is much more coherent, where in the arid Southwest, where climate exerts an extremely strong control over tree growth. So the correlation of tree growth from among trees is quite high in Colorado, Arizona, New Mexico. It's lower in, say, the Southern Appalachian Mountains, the Great Smoky Mountains, and so forth. It's kind of species dependent. There are species in the eastern United States that have a very strong inter-tree correlation. And this is a metric that we measure frequently, is the internal homogeneity of the trees and the cores within the site, within each site. But the differences, I mean, the climate signal recorded by the chronology in the Southern Appalachians is quite strong, even though the inter-tree correlation is not as strong as it is in Colorado. So that's a very important aspect of this.
Awesome, thank you so much. That's really interesting, and that's so cool that there's even an additional, that you're able to do so much at the different sites. I also had a question for Courtney, if that's okay, Lindsay?
Yes, go ahead, Anna.
Okay. So Courtney, my question for you was on the slide where you showed like the resistance, resilience, transition, or basically my question is about metrics overall. Like, how do you assess the effectiveness of those partnerships or monitor outcomes? I was specifically thinking like when you were describing how you sort of responded towards some of the like restrictions or reasons why people weren't able to necessarily use this information in their adaptation planning, and then you responded to that. What has been the response to things like the vulnerability assessments and putting that amazing amount of demonstration products online? Like, anyway, yeah, how do you assess, what are the metrics, and then what has the response been to sort of your addressing of people's concerns in that way?
Yeah, that's a great question. For the metrics, it's really, we've been looking at kind of the spectrum of strategies that people are choosing to implement in those demonstration projects. So are people really doing more resistance or resilience treatments, or how many are really starting to think about doing transition? And as you would assume, like most people, our current management can be really climate adaptation strategies and approaches. And so a lot of the efforts being implemented on the ground are those resistance and resilience. But then I think also seeing the number of new crazy ideas that people are starting to think of for those transition strategies, and going outside of the business as usual management and really thinking about things like assisted migration. We're starting to see more of that, and there's more acceptance, I think, of trying some of these transition strategies on the ground. And so those are some of the metrics we're looking at for just success of going through that process and really thinking about what can we be doing for the future. And then for some of the different monitoring of that, it just like we're tracking different seedlings, we're measuring responses and growth of what's planted, we're looking at how is the soil carbon changing and that sort of thing. And so they're just depending on what strategies people are implementing, we're using all kinds of different strategies to monitor the effectiveness of that. But especially at our ASCE sites, there's different researchers who are joining the projects who are really interested in, like, we have a site in Georgia and they're studying herpetology, and they really want to know how changing the overstory canopy is influencing the herpetology populations on the ground, and what does that mean for some of those local species. And so we're starting to look at that as well. And so there's a whole spectrum of ways we're thinking about monitoring some of these strategies.
Thank you, Courtney. So unless Anna has more questions, we still have time if anyone has questions. You can also raise your hand and we can have you join the conversation. But panelists are also welcome to ask each other questions if you have any. Yeah, so any questions from the panelists towards each other?
Hey, Lindsay, can I ask another question?
Yeah, go ahead, Mike.
Thanks. Anyone or whoever wants to chime in, feel welcome to. I was wondering, looking at the plot that Russ had shown, sort of that timeline of the percentage of Colorado or Western Colorado that was in drought and had the scale, the intensity of the drought also, in thinking about some of the things that Dave and Russ were also talking about with the standardized indices for drought and then the evaporation and precipitation intensity. Do we expect that are we experiencing changes in like the speed in which we enter drought, or particularly extreme drought? And then sort of the second part of that question is, for Courtney would be, is that like the speed at which you enter drought, or I guess Dave would have input too, is that something that trees or the local ecology would be sensitive to, would need to be something that would have to be adapted?
I mean, I would say we have seen that in the last several years, that the kind of onset of drought, both in 2018 and then, I mean, even last summer and then this summer, has been very quick because the summer conditions have been so hot. Whether that is sort of a trend that's going to continue or not, I'm not sure. But again, the increasing temperatures kind of put stress on things in new ways. Because last summer we went from the first time we had no drought on the map in like May and June after the huge snow, but then July, August, September last year was the hottest on record. Possibly will be surmounted by this year, I guess we'll see. But so some of those shifts are really rapid. But I guess I don't have a great sense for historically how that rapid, rapidity of the change has changed either. That'd be something be good to take a look at.
We kind of call it flash drought too. It's known as flash drought. And 1980 was a big time. May was pretty nice and June was terrible. And it was terrible the rest of the year. I think 2011 was a quote unquote flash drought, really summer onset drought. And so that's one of the reasons why we developed these seasonal precipitation reconstructions, to try to identify those kinds of rapid onset, warm season droughts, and try to get a better understanding of, well, their frequency of occurrence over time, and also what's causing them.
Yeah, that's a good point, because we've seen those. I was kind of thinking of here in Colorado, but yeah, we've seen some really bad flash droughts in the last few years in other places as well. Last summer in the Southeast, they had a really intense summer onset flash drought. 2017 up in like the Montana area, 2012 across like the entire Midwest. So, but right, whether that term was only invented, a decade ago. So whether those are kind of really stand out historically, I'm not sure, because maybe it just wasn't a thing that people were looking at in the past. But that's where, yeah, Dave's data can really give some insight into that.
Yeah, and then it has, implications for the phenology of our trees, and Dave can probably speak to this better than I can, but especially thinking about how those August monsoons can be really important for fall colors and all of our recreation. And so if we're not experiencing those, that can have big implications for, revenue that we're getting for leaf peeping and that sort of thing. And so changes in the phenology are going to be important. And then especially with the fires that we're dealing with, we have 10-hour versus 1,000-hour fuels. And so some of those droughts that occur so quickly and last for those longer periods allow for more of those 1,000-hour fuels and those really hot, dry conditions, so that when we get those lightning storms that then come potentially with the monsoons, then we can see a lot more of those wildfires starting as well. So those are other things to be thinking about.
Awesome. Thank you all so much for answering those questions. It doesn't look like we have anything else lingering in our Q&A box. So I will just wrap up here by, again, thank you so much to our three panelists today. It was a really interesting, really enjoyable, not only presentations, but group discussion afterwards. And really thank you for taking the time and energy to spend it with us and talk about change in Northwestern Colorado and in the Yampa Basin altogether, and for agreeing to stay on a little bit after time. And then I will just say again, our next webinar, the final one of the 2020 series, will be on October 22nd. And we'll be sending out some emails as soon as we get our last bit of logistics tied together. So you can put that on your calendar. And we look forward to hopefully bringing you all back to Steamboat next year if we're able to, and doing this in person. But in the meantime, stay safe and be well. And we look forward to continued collaboration in the future.
Thanks, y'all.
Thank you.
I appreciate it.
Thank you.